Sections 12.2 and 12.4 are grouped together because they both deal with prisms and cylinders. So 12.3 and 5 deal with the conic and pyramidal shapes, so we kind of cover these two together because they're about the same shapes. So reminder, you know most of this stuff. There's a couple things that may be kind of new, but you should know most of the things we're going to fill in here. So a prism is a shape that has two congruent bases, two congruent parallel bases. So if I have two congruent rectangles and could draw it better, then this is going to be a prism. We also could have like a triangular prism like is shown here. So you can have rectangular, triangular, any polygon. So I was trying to find a different one. So here we have 1, 2, 3, 4, 5, 6. This is a hexagonal prism. This one is a trapezoidal prism because the bases are trapezoid. So as long as the bases are congruent polygons, that's all that matters. So that's a prism. Cylinder, same idea, except the bases are circular. So we have something like that. So you should know those shapes, hopefully. The bases are the things that are congruent at either end. So if I had a triangular prism, like something like that, then my bases are going to be here, the front and the back. So what's really important to keep in mind with bases is that it's the two congruent polygons that are connected by rectangular faces, not necessarily what's sitting on the ground. So when we say base, we think about what's on the ground, but that's not necessarily true. Just like with an isosceles triangle, if I draw it this way and these two are congruent, the base is right here, not necessarily a side facing downward. So my bases are my two congruent shapes. With prisms, with rectangular prisms, it's kind of tough to know what the base is because all pairs of opposite faces are congruent polygons. So with a rectangular prism, you kind of need to be told what the bases are. But for any other shape, it's the two things that aren't the rectangles, basically. All right, lateral faces are all of the other faces. So if I kind of copy this same triangle again, triangular prism, then my lateral faces are all of the others, the rectangles that connect those two bases. For a cylinder, my lateral face would be that round one. I don't know if you call it a face because it's circular, but it would be like the wrapper on a soup can, basically. So all of the stuff that's not the bases is your lateral faces. And then your lateral edges, I'm going to use this same guy again, just so we can compare like things. Lateral edges are the edges of those rectangular faces. So my lateral edges are connecting between the two bases. So yeah, that's those three. Hopefully you already knew all of that vocabulary. One thing that might be new is you've probably only seen right cylinders and right prisms. So that means that they're not slanty. So basically think about a parallel to a rectangle would be a rectangle versus a parallelogram, where the parallelogram has a slant to it. And we saw that rectangles and parallelograms are both really similar because they both have an area that's base times height. But there are differences because the height is not an edge of this shape. It's going to be exactly the same idea for these. I'm going to use a cylinder for this one and do a right cylinder is one like this, where it's straight up and down like most cylinders you're used to seeing, and an oblique would be one at an angle. So this is like the parallelogram version of a prism or a cylinder, is we take the same two congruent circles but offset them so that my connecting face is now slanty. So altitude and height, I don't know why there's two boxes. Those are the same thing. So altitude or height is how tall it is. So I'm going to continue using this oblique one. Maybe I'll do both. So do that. That. So my altitude would be my perpendicular distance, because the bases are always still parallel. So my perpendicular distance is going to be my altitude or height. It's the same thing. So if you have a right prism or a right cylinder, then it's going to be the actual edge of the shape. So here, my altitude or height is the same as my lateral edge length. It's the same thing. Whereas if you have an oblique one, you end up with something called a slant height, which is like our slanted sides of our parallelogram. So I have this oblique cylinder, and this lateral edge is now a slant height instead of a height or altitude height. So yeah, that's basically, even if it's not a right shape, if it's an oblique shape, this height is still important because it's going to be used to find the volume. All right, so we want to find surface area and volume of these shapes now that we've got vocabulary and concepts down. Total surface area is just a matter of adding up all the surface areas individually, the exact same way that perimeter is adding up all the sides individually. Now, there's formulas for like surface area of a prism or of a cylinder, but really just think of it as being the sum of the pieces, because the formula is just memorizing, and why memorize? So if I think about this shape, I have 6 faces. So I have a top and bottom, left and right, front and back, and all of those come in pairs. So my front and back, I'm going to abbreviate front and back. My areas are 6 times 3. My left and right are going to be 9 times 3. And my top and bottom are going to be 9 times 6. And I have 2 of each of those. So I have 18 times 2, 27 times 2, and 54 times 2. So in total, that's 36 plus 54 plus 108 is equal to, that's 198. And we don't have any units, so that's it. Now, the formula is the perimeter of the base times the height plus 2 times the area of the base. And all we did was that exact same thing, but without a formula. So the perimeter times the height. Let's imagine that the top and bottom here are the bases, right? So my 2 times b, that was right here, 2 times b. My perimeter times height is just these two combined, because the perimeter is, so the perimeter of the base would be 9 plus 6, and then my height was 3. So I did 6 times 3 plus 9 times 3. That's the same thing as 6 plus 9 times 3. So the formula doesn't really add much value, honestly. All right, so second one, we've got a triangular prism. So we have the front and back are going to be, oh, we don't have our height. So, or we don't have the height of our base. We have the height of our prism is 6, but we don't have the height of the base to find this area. So the lateral surface area is really easy. We have 3 times 6 times 3, right? So that's, again, perimeter times height, because 3 times 3 is the perimeter, and h is 6. So my lateral surface area is 18 times 3 is 54. And then my challenge is finding my 2 base areas, because I'm missing this height. So we know that since this is an equilateral triangle, that half of this base is 1.5, and that this is a 30, 60, 90 triangle right here. So since this is the short side, we know that the long side is 1.5 times the square root of 3. So our area of this total base is going to be 1/2 times 3 times 1.5 root 3. So 1/2 times 3, that's 1/2 times the base, times the height is, well, let's do fractions so that we can just have fractions throughout. So instead of 1.5 root 3, let's do 3/2 root 3. And we have a front and a back, so we actually have 2 times that area. That's going to cancel out my 1/2 and my 2. And I end up with 9 over 2, or 9 root 3 over 2. I can't simplify 9/2. I can't add these two things directly because one has root 3 and one doesn't. So my total surface area would just be 54 plus 9 root 3 over 2. And without a calculator, that's as simplified as we're going to make it. That's our precise answer. And then maybe we also want to type that in the calculator and get a decimal approximation. So let me grab Desmos real quick. All right, so Desmos to the rescue. We have 54 plus division 9 square root of 3 over 2. So as an approximation, so we could say that's approximately, and of course I didn't pay attention to the number, approximately 61.8, whatever our units are. So again, kind of like it was in the last chapter, I want us to be able to kind of fluidly work with both precise or exact answers and with approximations. So it'll be common that I want us to give both of those answers for these problems. All right, so surface area of a right cylinder. We need, again, to add up all the faces. Here there's 3 total faces. There's top, lateral, and bottom. And our top and bottom are the same. So we end up with the same formula, perimeter times height plus 2 of the bases. But again, I think of it as just adding them up. So our diameter is 8, and our height is 6. So our area of our base is going to be pi times 8 squared over 4. That's pi d squared over 4, or we could have just done pi r squared. Either way, we get 16 pi for each of the 2 bases. So we have 16 pi on top and 16 pi on bottom. So far we have 32 pi plus whatever the lateral surface area is. And the lateral surface area, there really is no way to think of it other than this circle kind of extruded into the 3rd dimension to make this wall around the cylinder. So it's going to be 2 pi r, or pi d, so that's 8 pi, times the height of the cylinder, which is 6. So that gives us 48 pi for the lateral surface area. So the base is pi r squared, or pi d squared over 4. And then our lateral surface area is 2 pi r h, or pi dh, depending if we're thinking about diameter or radius. Same formula, just different format. So we have 38 pi plus 32 pi plus 48 pi, and in total that gives us 80 pi. And that is a precise answer. If we wanted to approximate it, we could put that in the calculator and do 80 times pi, and we get about 251.3. About 251.3. Again, we don't have any units, so we don't worry about that. All right, surface area of oblique cylinders. So here, I think the most important thing to remember is that if we have a rectangle and we have a parallelogram, So think of this guy and this guy, and they have the same base and the same height, then there's really no difference in those two shapes, right? They have the same area, they have the same perimeter. It's just one is kind of slanted over versus the other one. Sorry, so they have the same area, not the same perimeter. So the analogy for volume would be that it doesn't matter that it's slanty, just like it doesn't matter for area here. But the perimeter does matter because the shortest distance between the bases would be a straight line, whereas a slanted line is going to be longer. And the further over we slanted it, the longer these slanty sides get. So perimeter here is equivalent or analogous to surface area here. So what we need to do is still add the two bases. So we have two bases, but then our lateral surface area, the part that wraps around, instead of being 2 pi r h, we don't actually use the height for this one because we're not wrapping around the height, we're wrapping around the lateral surface. So our lateral surface area for an oblique cylinder is going to be very similar, but instead of h, we're going to use the slant height, which we call L, usually as a script L. So this h is 10 and this L is 12. So here it would be 2 pi r L or pi d L. So here we have the radius, so we'll use the radius version. So 2 times the base area. That's 2 times pi r squared. And then 2 pi r L, that's 2 times pi times our radius times our slant height. So slant height you may have seen before in formulas for pyramids. So you've probably seen that a couple years ago when you dealt with surface areas of pyramids, I think. All right, so we have here 18 pi. And here we have 672 pi. And our total then would be 90 pi. Or if we wanted to approximate 90 pi, I'll just change this 8 to a 9. We would get about 282.7. Again, no units. So that's surface area. But the idea is we're just adding up all of the different faces. The only thing that's at all challenging with that then is this lateral surface area and dealing with a right versus oblique cylinder. For regular prisms, or for prisms, remember that we now know how to find the area of a regular polygon. So the stuff that we saw in chapter 11, where we found areas of regular polygons, can definitely show up here as well for finding this area of the missing faces, of the missing bases. All right, so second topic for today is volume. Volume of a cube. Find the volume of the cube with a side length of 3. So the nice thing about prisms and cylinders is they are uniform throughout as far as their cross-section parallel to the bases. So in the last lesson we talked about if we kind of sliced through anywhere with a plane, the cross-section here is always going to be the exact same shape as that base. We're going to get a congruent square anywhere we slice through this thing. So let me actually bring up a visual real quick because I think it'll help us to visualize this. Okay, so I just went and sketched up in Onshape real quick a prism that has a regular hexagon as its base. And what I wanted to do was look at making a cross section. So in engineering software, we have something called a section view, where I can basically slice through the part like this and look at it at different elevations and say, what would it look like if I just cut it off right there? It's not actually removing the rest of the shape, it's just letting me see that inside part of it. So you can see here that no matter where I move throughout the shape, then the slice that I'm getting is always this exact same regular hexagon. But what I thought might not be quite as obvious is if this is an oblique prism. So this is a right prism, it's straight up and down, but what I'm going to do is modify this a bit and change its direction to go this way. So now this is oblique. So if I looked at it from like the front, it's like this. So if we do a cross section of this one, what I want us to see is as we slice through, it doesn't matter where we slice through as long as we're slicing parallel to the bases. Every single hexagon is still congruent. So every slice that I get throughout this whole shape is the exact same hexagon. It doesn't matter that this is slanty. I get the same exact shape all the way throughout, no matter where I go. Okay, so that's what I was hoping would help us visualize the idea here, is that it doesn't matter, kind of like I was trying to explain before with the rectangle versus parallelogram, is that it doesn't matter how slanty the shape is when we're talking about volume. I was getting ahead of myself with surface area, but for volume, the slantiness does not matter. All that matters is the normal formula, which is the area of the bases times the height. So let's say that my base is this right here. And the idea is for a prism, that base, that area, is just stacked on itself, like over and over and over and over and over again, up to the total height of the shape. So this base is 3 by 3, so I know it has an area of 9, and then if I wanted to think of it as making little cubes, then I could stack up 3 cubes that were also 1 inch or 1 whatever high. So I take that 9 and multiply it by 3 and get a total volume of 27 cubic units. So let's say this is 3 inches. Then I would get 27 cubic inches. So kind of like we talked about in chapter 11 that we measure area in little squares, we measure volume in little cubes. So that means if I had 27 cubes that were 1 inch on each side, then it would fit perfectly into this bigger cube that's 3 by 3. So hopefully that visual helped. I don't know. Yeah. All right, so volume of prism, we have an equilateral triangle base. So we have a height of 6, and we have an edge length of this triangle of 12. We saw in an earlier example that we can split this, make half of the base 6, and then the height would be 6 root 3. So we know that our total area is just the area of the base times the height, because we're taking that base and slicing it and putting enough to fit 6, right? We're putting slices of it to add up to 6 height. So our area of this triangle is 1/2 base times height. So that's 1/2. The base of this triangular base is 12. And the height of it is 6 root 3. So 1/2 of 12 makes 6. So I get 6 times 6 root 3 is 36 root 3. And then to find the volume, I take that base area. So this is my base area, and I do my base area times the height of the prism. So that's 36 root 3 times 6. And again, hopefully this is all review. These are formulas you should have seen before and problems you should be able to work already. 6 times 36 is 180 and 36. So that's 216 root 3. And again, that's going to be in cubic units. So that's a big difference between surface area and volume. Is these things were all measured in square units, even though they didn't give us units, because we're measuring how many little squares would fit on the surface of that to completely cover it, so like wrapping paper. Whereas here we're talking about how many little cubes would it take to fill up the space inside the shape. So if we wanted to estimate 216 root 3, we we can go back to Desmos and do 216 root 3 is about 374.1 cubic units. And then volume of cylinder, same exact thing, is the area of its base. So this is literally the exact same formula. The area of the base, that's a bad B, times the height of the cylinder, where the height is the actual height, whether it's an altitude or a lateral edge. So there are no slanty ones here, but if we had an oblique cylinder or an oblique prism, this h would still be the height that we care about. It wouldn't be the slant height, it would be the altitude, like the perpendicular distance between the bases. All right, so our base area, we have our diameter, so it's pi d squared over 4, so pi times 6 over 4, and then times the height is 14. So I can do some simplifying. This is 2 and 7, and this just makes a 3 and a 1. So I have 6 times 3 times 7 is 42 times 3, 126. So I get my precise answer as 126 pi cubic units. Let's call these centimeters, and we'll make this cubic centimeters, which is approximately 126 pi 395.8. So about 395.8 cubic centimeters is how many would fit inside. All right, so that hopefully, again, was just a refresher of how we do volume and surface area of these two kinds of shapes. Shouldn't be anything new there. The one maybe new thing is where, like I said, we have here a regular hexagon base or a trapezoid base. You need to use the way we learned to calculate areas of those shapes and then multiply by the height, or if we're doing surface area here, these are volume. So yeah, if you're doing volume, multiply by the height. Yeah, that's pretty much it. So there's some practice here for you to try. We even have like a composite figure, I guess, where we're subtracting one prism from another. But try those out, and hopefully this is all just familiar review stuff.